Okay, this short, I hope, video just takes it a little further in trying to explain rates. Again, we're going to look at activation energy and our potential energy diagrams, and we're going to see how those can allow us to explain how a catalyst works. And we're going to look at another type of diagram. It's called the Maxwell-Boltzmann distribution, and these distributions can allow us to explain both catalysts and temperature changes and their effect on rates. So we can get started on these right away. First of all, if you recall a potential energy diagram, there it is. So here we have our reactants at some energy state. We have our products at a lower energy state. So this is an exothermic reaction. And this would be our activation energy. So the energy required to raise our reactants up to some level where we can form this activated complex. And it's that activated complex that essentially allows the reaction to proceed and get our products. And here, then, we're going to have a delta H value. And that delta H is negative, and that's why that's an exothermic process. So remember potentiality diagram and what it so what we can look at now is a potentiality diagram and how we can illustrate what a catalyst does. If you remember, by definition, a catalyst lowers the energy required for a reaction to proceed. And so how does it do that? Well, essentially it just provides a new pathway, and that new pathway has a lower energy. And this often occurs in a series of steps. And so this would be a catalyzed pathway. And if it's a series of steps, what you might have is one activated complex, again not very stable, but energetically lower than the original activated complex up here. And so then that activated complex again becomes more stable, but you form another or second activated complex, and it then proceeds to form your desired product. It's not uncommon for catalyzed reactions to occur in a series of steps. The main thing is, here is our activation energy in our original reactions, about like that. So that's a very high activation energy. Whereas in our catalyzed reaction, the activation energy is lower. So lower activation energy lowers the energy required. So that's how a catalyzed reaction works. And you can show that to some degree with a potential energy diagram. Now the other diagram mentioned was this diagram known as a Boltzmann distribution. And so a couple things to make note of here. Number of entities. This is basically an amount of particles. And so we just have some amount of particles, and then we have energy. And so essentially what it means is at any given point on our curve, say here, there's a column that indicates the number of particles at that energy. And so the distribution basically is spread out, so you have a whole bunch of different particles at a series of energies. And because it's a potential energy diagram, what we can show here is the activation energy, and it's on this energy scale. And the important thing to recognize about a Boltzmann distribution then is that what you have is a whole pile of particles, all these particles in green, that are below activation energy. And if they're below activation energy, they're not going to react. Right? They don't have enough energy. So they're just buzzing around, and they could be colliding with appropriate orientation, but they're not going to react because they're below activation energy. And above activation energy, you have particles that have the potential to react, so could react if orientation is sufficient, if if they collide appropriately, because they do have sufficient energy. So there's always some component of a given reaction where they may actually, products may be formed, because there's always molecular motion, and some of those particles will be at or above activation energy. So anyways, that's a Boltzmann distribution. Notice that the predominant, most of the particles are in the green part of the curve, below activation energy. And again, that should make sense, because reactions do require some input of energy before they proceed. So how can we use this distribution to explain things? Okay, so what can we do with this Boltzmann distribution? Well, one thing we can explain is the temperature effect. So we want to see a temperature effect on rate. And so again, if we recall, here's all my green particles, or my green area under the curve, all these particles that are at or above activation energy. Now, if I increase temperature, what am I going to do? Well, if I increase temperature, I'm increasing the average kinetic energy of all particles. And so what's that going to do to the curve? Well, it's going to make the curve shift something like this. We're going to see potentially an increase in temperature followed by an increase in the average kinetic energy, and so we're going to shift the entire curve off to the right, and it's going to look something like this, maybe a little a little off, but it does look something like this. And don't forget, the activation energy hasn't changed. Temperature does not change activation energy. And so how have we shifted this, or changed this distribution? Well, we've sort of shifted everything a bit to the right, and now we have more particles under the curve. So more particles at or above activation energy. And if we have more particles at or above activation energy, more particles are going to collide and have successful collisions because they're at a higher energy, and so the rate would increase. So it is important to realize this with this Boltzmann distribution and temperature effect. Temperature increases the activation energy of all particles. It causes the curve to shift a bit to the right, and you end up having more particles at or above activation energy. The other thing you want to try to indicate here, and I haven't done a great job with this one, but you do want to indicate that you want to try to indicate that both of these curves have the same volume, because we haven't changed the amount. The amount of particles has not changed. That would in itself have an effect on rate, and we're only looking at a temperature effect. So both these curves should have the same volume under the curve. It's just that a greater number of particles at the higher temperature are higher up the curve. They're closer to activation energy and more above activation energy. So that's something important to realize or remember. And I'll just label this one as T2. This is T1, and don't forget T2 is greater than T1. So Boltzmann distribution drawn this way, it does allow you to explain a rate effect, how an increase in temperature causes an increase in rate of reaction. The other thing, as I mentioned, a Boltzmann distribution can do is explain the effect of a catalyst. So if you remember, again, a activation energy, certain number of particles at or above activation, it gives rise to a certain rate. Well, if we increase or add a catalyst, we can change the activation energy. And now notice the activation energy is less. That's what a catalyst does. And lo and behold, I don't shift the curve at all, but I still get more particles at or above activation energy because the catalyst lowers activation energy. So we don't shift the curve, we shift the activation energy. And that's activation energy to EA2 with the catalyst. So once again, more particles at or above activation energy, more particles under the curve there, more particles involved in successful collisions, the rate of reaction will increase. So potential energy diagrams and Boltzmann distributions, you can use both of these schematic diagrams to explain and discuss temperature effects on rate and catalyst effects on rate. And that concludes this video.